dams and discontinuities, the fragmentation and functional disruption. So this is not gonna be necessarily a tropical system lecture. It's the problems from dams are global, and we're gonna go into a global perspective of them. Yeah, so let's dig into it right now. Oh wait. Yeah. So there are a lot of influences or impacts on the natural flow of waters. It's not only dams that are affecting the rivers, although they are huge drivers of impact. This I'm gonna keep for later because basically the whole lecture is on them. But we have other impacts. We have, for example, water storage. So basically, the use of water for industry and agriculture reduces the base flow of water, and that has effects. So reduce oxygen, creates algal blooms, changes of habitat, and many other. And less water is available for the services and the ecosystemic connections that a river has, which is not only the flow of water, but also the riparian forest and all the animals that need water for their lives. Then we have engineering constructions like culverts and weirs, which make migration of organisms up and downstream difficult. So this is a version of connectivity obstacle, not as big as a dam, but it still has effects. Then we have channeling, which is basically when we take a river or when a river is taken and it's isolated from the hyperharic zone because we build or make them run through a concrete or other man-made impervious substrate. So that's channeling, and we see it a lot of when the rivers pass through cities. And, well, a lot more of human impacts on natural flows of water. But, as I said, one of the most important ones and a global problem that we have are dams. So, I am close to this topic specifically because some of my professional life was devoted to working with dams or in relation to it. And there was a particular event in Colombia with a huge dam, which was actually the first slide from the presentation. You saw a huge dam there. That's called Hidroituango. So that river passes through some really important biodiversity spots, but its construction had some problems, and in 2018 one of the tunnels they were building that was connecting the water flow to the engine rooms collapsed due to an avalanche, so it was locked. So basically the water could only run from the upper part of the dam, and it wasn't fully finished at the moment when the accident happened. So what that entailed is that in the upcoming wet season, the water will overflow over it and will basically destroy the dam and would have basically destroy villages and cities downstream from it. Well, it didn't came to it, but what happened, they started some regulation of the water during those days, and what they had to do was basically close the flow of water completely. So they closed a river. Imagine if you went to the Rhine and you saw it completely dry from one day to another. So that happened they had to do it to do the reparations inside the collapsed tunnel, and they had to do it for weeks at a time. So when that happened, was crazy for the organisms that live in the river, in particular fish. So I was called to do fish rescue in the river. Here already was some flow in the river, but what happened, it was so low that the river was trapped in lakes at the sides of the river, so we had to go there, collect them, and take them back to the main channel, because the flow change was so drastic and so fast that they just couldn't migrate to the main channel. Yeah, so that just as a small story, and to tell you that South America is an hydroelectric powerhouse. Many of the countries get their energy mainly from hydroelectric power. If you remember, we saw that precipitation and water availability is huge in South America. And yes, and I've also been working in fishing management of reservoirs, because the reservoirs that are created with dams that are usually used for fishing in Colombia. So I had to do a lot of with the local communities, and the impact assessment of dam building and infrastructure construction. So I've been talking a lot of dams, but let's see how one works.
Energy, you need two things: an abundant supply of water and an elevation to drop it from. Building a dam creates both. The dam creates a reservoir which stores water until it's ready to use. Water enters the generating system through a series of giant intake pipes. It then travels down a steep pipe called a penstock, creating a massive column of water with a huge amount of force. At the base of the penstock, the water passes through a turbine. The giant blades rotate the drive shaft in the turbine, which is connected to a large generator. This converts the mechanical energy into electricity. The electricity travels along high-voltage wires to transformers, then onto transmission towers, where it connects into the provincial power grid. After passing through the turbine, the water continues through the tail race, where it rejoins the river below. A hydroelectric dam is a remarkably simple, sustainable, and clean way to generate huge amounts of power.
All right, so that's basically for us to understand the engineering of a dam, how it works. And well, dams are, let's say, quite necessary in our current scenario as humans. Well, basically, they give us hydropower energy. They are also important for flood control. So when we have we can manage how much water and when does it come out of it. So we can manage the flood downstream. It's important as a water reserve. Most of the drinking water that we have, even in this region, comes from dams that we do. I think, if I'm correct, all of this region, the water comes from dams. There's tourism around them. Basically, you have the Eiffel close here, and all of that is a dam. Economic development and drought management. Yeah, so it clearly has advantages, but it also has disadvantages on how they're currently done, and dams are really ancient. We have been doing it for hundreds of years. There are some new technologies that are changing the disadvantages a little bit, but we are not quite there yet. So there's community displacements, and when we build a dam, we're gonna flood huge areas, and there's people that live in those areas are gonna have to move somewhere else. There's environmental damage, loss of biodiversity, changes in the fluxes of sedimentation, changes in water quality, and economic cost. But dams and hydroelectric power is still highly important. Just now, during the COP30 that was held in Brazil, the EU agreed to a cut in 90% of emissions by 2035. And to do that, what do we need? We need green energy. And one of the most sought after green energies is precisely hydroelectric power. So it's not a problem or something that is going to change in the future. It's probably going to increase. So we need to understand how they work, and as scientists give feedback to this whole system that is going to keep growing to keep humanity afloat. So how water powers the world? So what we're seeing here is basically the amount or the percentage of energy that comes from hydro. And what we're seeing is, yes, South America, a big percentage of the electricity comes from hydroelectrical power. Parts of Africa, in the Congo basin, also. Southeast Asia, so there's no surprise that is where more water availability we have, huge rivers. So in the tropic belt, but also in Europe, it's quite important. Here, really dark is Norway, which actually 100% of its energy comes from hydro. But Norway is a particular example, because do you know what is the biggest export, or where does the Norwegian kingdom money comes from, or the hugest export, the hugest economic line of Norway? Yeah,
The fishing industry.
that's the second. Yeah, but the first is oil. So their whole country runs in hydro, but they export oil. So it's a bit of a funny situation they have going on there. But all right, so Europe is highly important. Not just in this graph what we're seeing. Okay, and as I said, in terms of the future, things are looking quite interesting. What we're seeing in this graph here is the current hydroelectrical power, either in dams or canal, which is basically a different type of hydro, but it also implies the diversion of the channel. Yes, but it doesn't create the dam. You just take the entire flow and pass it through a turbine. So this is how things currently look with the spots. But with the colors, what we're seeing, and this is a really engineering paper, so it's the unused profitable potential. Yeah. So the unused hydroelectrical power that is for us to tap to and make profit of it. Yes. So where are the places where with the hugest potential? So the temperate northern region, so northern Asia, so Russia, Canada and the States, and Southeast Asia, and big parts of Africa and South America. It is said that the hugest potential for new hydropower development is Asia, by far, as you see in this graph. So that's the current picture for the years to come. We have a lot of hydropower to use, but if we use it all, there's gonna be some problems for the rivers worldwide and the natural ecosystems. Okay, so now that we're gonna delve deeper into these effects of dams, I really need to have these fundamentals of lotic ecosystems clear with you. And one of the clearest fundamentals of it is the 4-dimensional nature of lotic ecosystems. So if you're gonna read one of the papers I'm gonna put in the suggestions, read this one. It's really short, well written, and it's old, no? 1989. But here, Ward already was trying to give us a synthetic framework for lotic ecology. Many of the things he observes there or he puts together, they're gonna come really easily for you, and it's the foundation of a lot of the research that is done in lotic systems. So these 4 dimensions, we already been talking through through the lecture about it. We have been delving in each one separately or together, and but he made the synthesis of that and put it together in this quite simple graph. And what he says is basically that the heterogeneity is manifested as interactive pathways along 4 dimensions. So rivers are really heterogeneous systems, highly dynamic. When you think on a lake, you think about peace, like nothing is happening. There's or everything is happening, but below the water surface. But you thinking on a river, maybe you're thinking on rapids, water flowing, moving, changing. And this is not happening only in the longitudinal dimension, so in the channel, but it's also happening in the lateral dimension, so the channel plus the riparian and the floodplain. So together with the terrestrial system in the lateral dimension. Then we have the vertical dimension that we discussed last time, where we have the channel plus the aquifer. So we have the hyporheic zone. And the fourth dimension is the temporal scale that we have already touched a little bit when we were talking about the hydrographs. So how flow changes during the year and during the days and in time. So basically the temporal scale. The smallest piece of or the smallest scale, when we're talking about minutes, seconds, we see a behavioral response. So when some of these dimensions change, or we see a change, or organisms react to it. But in the biggest temporal scales, we see evolutionary change. What is an example of evolutionary change from the studies that I told you before? In this 4th dimension, yeah?
The marine systems.
Correct. Yeah, the Western Amazon study. So that will be an evolutionary change level of in these 4 dimensions. Okay, so those are the 4 dimensions. Already in this paper that is 36 years old, Ward was already envisioning that the emerging discipline in those days of landscape ecology will provide a fresh perspective for lotic ecologists interested in the interactions between river channels and adjacent terrestrial and aquatic systems. So in those days, it was only like the baby steps of landscape ecology, but it has come really far. And basically, nowadays allow us to understand local to global change. And in the next slides, I'm going to be using a lot of landscape ecology examples in a global scale to see how dams influence lotic systems around the world. So, damming the world. In this study from Shang in 2023, basically they created a database with the dams of the world. And they estimated 2.8 million dams with reservoirs that are more than 100 meters. So really, they went from really small dams that are created in agricultural escapes to the biggest ones. So that's why they have 2.8 million ones. And these dams around the world create an area of around 500,000 kilometers of rivers and canals for navigation and transport. And there are 35,000 major dams in the world. And that's what we're seeing in figure A. And in figure B, what we're seeing is the catchment area of the dams of the world. So when is the whole area of the catchment before it reaches a dam. And basically we're seeing that almost half of Africa is dammed in a way. A lot of South America catchments are dammed. North America, big parts, almost over Europe, catchments are dammed. And here, okay. So that in terms of the global aspects. And this study from SARF in 2015 focused only on the major dams on the world, but he gave us the 35,000 number that was already done. So those are the blue dots that already exist. But in 2015, he made this map foreseeing the planned dams. So and he found that for 2015 there were 3,700 major dams either planned or under construction. So what we're seeing is that the dams are not stopping; they are rising around the world. So it's a constant and pressing concern. So, what are the main challenges of dams for rivers as life-sustaining ecosystems? So, this is a question for you. What do you think is the major challenge that a dam brings to an organism living in a river? Either living in a river or living in the forest of a river, or basically a lotic organism. What challenges do a dam brings? Yes?
There are obviously organisms which migrate in the river depending on what the yield or something, and they are migrating upwards normally, and all of a sudden they can't because there's a wall in their way. It's obviously a massive change, and they can either change their way of living and lay the eggs there, for example, or they just die.
Yeah. Well, yeah, that's a really important part of the challenges. That is basically connectivity. So basically the ability of an organism to be able to move from one point to the other in the longitudinal stretch of a river to complete its life cycle, or just to live on a system. And that one is key, and we're gonna start with that one, and then we're gonna see some other challenges that a dam brings. And to go with connectivity and fragmentation, we're gonna start with this paper from Grill in Nature, which basically what they did is mapping the world's free-flowing rivers. And to do this mapping, what they did first was creating a framework to know what is a free-flowing river, or in their way to create a index of connectivity in the river systems. And what they did, what is important to understand here is that they divided the river in river reaches. So let's just go slowly in this box. They draw hydrographic framework. So they have the river reach, which is the smallest element in the river network, and unit for the calculation of the connectivity status index, which is what they developed in this paper. And the river reach for them is the smallest hydrographical element in a river network. For them, that's their assumption. But it can be really smaller if you see it in other ways. Then, the river has a linear feature that consists of multiple river reaches. So, multiple river reaches. And they use the 4 dimensions of WART, longitudinal, lateral, vertical, and temporal, to see how one reach was connected to the other, and if this connectivity was broken by a physical barrier. So that's their assumptions and how they perform this coefficient, this index. Basically to see if there's a physical barrier and how many reaches breaks behind it. Okay. So they have the hydrographic framework, the connectivity dimension, the 4 dimensions from WART, and the free-flowing river status. So a free-flowing river status is determined on the basis of the connectivity status index. So only rivers with high levels of connectivity, over 90% throughout their entire length, are considered free-flowing in this study. Okay. So the main human interferences with the 4 dimensions of fluvial or river connectivity. We have the river fragmentation, which works in the longitudinal frame. We have flow regulation. So remember that the dam actually at the reservoir manage the flow below the dam. So the flow patterns change, and that changes the pulses of water that generate the lateral connection. Water consumption. There's many times there's water taken from the reservoir, not only for the hydrological power, but also for giving water to agriculture, industry, and human use. So it has pipes connected to cities, and the water doesn't flow normally as it will do in its catchment, but is diverted to other catchments or uses. And then we have infrastructure development in riparian areas and floodplains. And that breaks the lateral and longitudinal connection. And these are the interferences that they use to assess connectivity changes in this study. So, the Integrated Connectivity Status Index, CSI, is the ability of a river to flow and exchange water, sediment, organisms, and energy without being blocked. And it goes from 0 to 100%. That's what we needed to know before looking at the results. So, what are we seeing here? We're seeing the Connectivity Status Index of the world's rivers reaches. And we're seeing on a scale of CSI from 0, red, to high in blue. And the darker the blue, the more connection. So what can you tell from this map? What is happening with the fragmentation of the rivers in the world? Where are they more fragmented, where they have less connectivity? Redder, less connectivity. Well, basically, North America, Europe, India, and what is the biggest relation that you can think with these regions of the world and high fragmentation and loss of connectivity? What is happening in those areas of the world?
We saw before that there are a lot of dams there in these regions.
And why do we have a lot of dams? Basically, is a lot of human development. This is basically the economical centers of the world, no? The United States, richest country in the world. A lot of the industry of the world is going on there. Europe, same stuff. India is the economical powerhouse of Asia. And China, of course. And, well, if you need energy and you need hydroelectric power, then you're damming and fragmenting your rivers. And that's basically what we're seeing with that pattern. But also, in terms of connectivity, where do we see the highest connectivity or the least fragmentation? The Amazonas. Yeah, the Amazonas. The Amazonas is really important in that regard. And also the Congo and some parts of Southeast Asia. What is this related with is the inverse of the other part. Is the human development is not so big in these areas. But there are some other patterns or reasons why it's not so developed in terms of damming there. What other things that you imagine could be a reason? If we see in the Amazon, the Congo, the northern part of North America, so Canada and Alaska, and the northern regions of Russia untouched, and Papua New Guinea also. What do they have in common? Well, they are just geographically really isolated and far away, and it's hard to bring power lines from these really far rivers to the main cities. That's one thing. The other thing is that the main sections of rivers, as the Amazon and the Congo, are so big that the technology is just not there to make a dam and to dam the entire Amazons. Lucky that is like that, but that probably will change in time. Well, that's what we saw in this graph. Now, in this graph, we're seeing the dominant pressures for global river reaches below the 90%, 95% threshold. So rivers that don't run freely. So we're seeing the dominant pressures of it, and we have different pressures, and them are, let's read them. We have the DOF, and what is the DOF? It's huge. It's almost 70% of the dominant pressure for the connectivity. And the DOEF is the degree of fragmentation, which is basically the amount of blockades to the transport and free flowing. So physical blocks. Then we have the DOR, so it's the degree of regulation. So how much the flow is regulated by dams. And then we have sediment trapping. And these three things together are the major drivers of stopping or the free flowing of rivers. But this, we need to know about this study and remember that this was not specifically targeted to dams, but to all type of river fragmentations in the systems. But what they found is that dams in particular are almost 90% in charge of fragmenting the connectivity of rivers around the world. And because the fragmentation is mainly driven by physical dams, the regulation of water is done by dams, and the trapping of sediments is done by traps. There's other drivers like consumptive water use that is not necessarily done by dams. Water can be taken from other sources. And the urban areas was also one of the things that I studied. So basically the urban areas constructed in the riparian forests. And now, in this other map, what we're seeing is the map of the world's free-flowing rivers. So the true flowing rivers in the world that still exist are basically running, as we said, in the Amazons, Congo, Northern Asia, and North America. And some of them in Southeast Asia. In Southeast Asia, there are really a few, and there are only two reaches that are still free-flowing that come from the Tibet and pass through Myanmar in particular. And the Amazon is still free-flowing. But basically Europe and the United States, North America, are having a lot of passages that are being broken. So what does this entail? So there's a special concern in the loss of connectivity for very long and long rivers to the sea. So there are many rivers that they are blocked, their way out to the sea is being blocked, and the life cycles of many aquatic organisms, freshwater organisms, is actually between the two systems. And one of the key examples from this is this fish, which is the salmon, that maybe you know that they go to the sea to grow, but they need to go back to freshwater to do the reproductive part. So when they find a dam, basically they cannot continue their life cycle. So other thing, and this is not only the salmon, we have examples from the tropics and many other systems. So also with the numbers reduced to only 37%, very long free-flowing rivers, that means more than 1,000 kilometers, are only in remote areas now of the world. which are difficult to exploit economically. So the Arctic, that's what I was telling you before. Other important thing is that the remaining free-flowing rivers, so the ones that we still have and that we should think about protecting and conserving, these rivers that still run free deliver at these proportionally high levels of certain ecosystem services. So most notably the inland and floodplain fisheries, the sediment transport, and biodiversity. So imagine if we were blocking the Amazons on some of the Southeast Asian still free-flowing rivers, we were basically trapping the entire sediment load of the Amazons, and we will be changing the nutrient flows of the oceans. And the last two remaining very long fresh flowing rivers in Southeast Asia are called the Irrawaddy in Myanmar and the Salaween. Both pass through, are born in the Tibet and pass through Myanmar, and they are critical sources of protein, and they maintain the food security for millions of people, and they are home to really important biodiversity and flagship species as this river dolphin that only lives in those two rivers in Myanmar. And to finish, what happened when we see, or what conflict do you see from the profit potential that we see in this graph and the graph that we saw with the free-flowing rivers, or the still existing free-flowing rivers in the world? Well, basically the remaining free-flowing rivers of the world are in the Amazon basin, Southeast Asia, northern Asia, and North America. And precisely where the still free-flowing rivers are is where the potential for hydroelectric power lies. So if we are to use this potential for a hydroelectric, we are going to dam the free-flowing rivers of the world, and we're gonna change biodiversity, sediment fluxes, and the biggest or the most important ecosystem services of the free-flowing rivers in the world. That's the main conflict that we see here. And an example of one of the last free-flowing rivers in Europe, which are really few, because we have been damming European rivers for hundreds of years now, is the Vjosa, which runs through Albania, and it became the first wild river national park not long ago. And it's a beautiful system that holds really interesting biodiversity and endemic species. And it would be nice if you read a little bit about it, and there's a lot of activity surrounding that river. And we're gonna leave it like that today, and we will continue with the lecture next time with another study case and to close on the dams.